Okay, so starting from today lecture, which is lecture number 16 and chapter number 9. Okay, so in the previous class we already discussed about the Stirling cycle and Ericsson cycle, and I hope you have some understanding about it. So today lecture is also related to gas power cycle and from Ericsson and Stirling cycle, and today we will try to solve some problems. Okay, so coming towards the first example, which is 9-2, the thermal efficiency of Ericsson cycle is the highlight of this one. And using an ideal gas, so you have to just read the statement. Using an ideal gas as a working fluid, show that thermal efficiency of an Ericsson cycle is identical to the efficiency of Carnot cycle, operating between the same temperature limits. Okay, so previous lecture we already discussed about it, that if we are operating between the same thermal limits, that is the highest temperature and the lowest temperature, so the thermal efficiency of the Ericsson cycle and the Stirling cycle is equal to the thermal efficiency of Carnot cycle. Okay, so today we will prove about it, that how this will be equal to Carnot cycle efficiency. Okay, so before this, we have to just correlate one of your previous knowledge from thermodynamics. So if you can just go to chapter number 7, and I think it is straight. Okay, so these are the relation, that is the S2 minus S1 integration CVP dt by d plus R log of V2 over V1. I hope you already know about this relation. So this relation can be valid for the isothermal processes. So either this will be 7-31, or if you have to write in Okay, so again, starting from the TS diagram first. Okay, so as you already know about it, the TS diagram of Ericsson cycle. So in the Ericsson cycle, there are isothermal processes between 1 to 2. So the temperature is constant, then there will be a constant pressure regeneration process. So it will be 3 point, and then from 3 to 4 isothermal process, and then 4 to 1 again it will be the constant pressure regeneration process. Pressure is equal to constant, pressure is equal to constant for quantity. Okay, so from this we can say that you have to know that efficiency equation is equal to 1 minus Q out over Q in. Okay, so we have to find the value of Q out and Q in for the isothermal process. So we can say that Q is equal to T delta S. So this comes from your chapter number 7 from thermodynamics 1, that it is equal to T delta S. Okay, so from the equation 731 and 732, which I already told you, and that which is valid for the isothermal processes, so we can say that delta S is equal to Cp log of T final, you can say, and that is as any state point, and T initial minus gas constant log of T final minus T initial. Okay, if it is an isothermal process, because we are talking about process 1 to 2 and 4 to 3. So these are isothermal process, so this term automatically eliminates. Okay, because isothermal condition Tf and Ti is equal, both are equal. Okay, so now we can say that delta S is equal to minus R log of, so you can say Pf final and P initial. So now another equation from this one, we can say that Q in is equal to, so the Q in is at the TH, which is at the highest, and Q out is at the T lowest. So we can say TH and delta S is between S2 minus S1. Okay, so we can simply put this value of delta S into this one, which is the Q in equation. So it turns out to be TH minus R log of P2 over P1. Okay, so if I just rearrange it and if I just shift from the denominator to above and numerator to the below, so it's automatically cancel the negative sign. Okay, so from the mathematical knowledge, we can say that R into TH log of P1 over P2. Okay, this is the Q-in equation for isothermal heat addition process. Okay, so now in the similar procedure, we have to develop the Q-out equation as well. Okay, so Q-out, we can say that it is at the lowest temperature, so TL S4 minus S3. And also this is negative because the heat is rejected from the system, so we have this at negative sign. So minus TL, and again you have to put the delta S value, so you can say minus R log of P4 over P. And if I just rearrange it, it turns out to be R TL log of P4 over P3. Okay, so now Q in and Q out equation are known to us. So you have to note it down, then we will move to the next one. If you have any question, you can also ask. Okay, so now simply put the values of Q in and Q out in your equation, which is for the efficiency. So it turns out to be 1 minus gas constant, and this gas constant can be any, if you are using helium or if you are using hydrogen, so you have to put the value of gas constant on it. Okay, when we are going to solve the problems related to the Stirling cycle and Ericsson cycle. B3, and then R TH log of P1 over P2. Okay, so from here we can easily eliminate R, and if you just go back to your previous lecture, you can easily find from the PV diagram that your pressure at 1 is equal to pressure at 4, and your pressure at 3 is equal to pressure at point number 2. Okay, so if I just put the values of these pressures, and we can say that this can easily be cancelled. Okay, because if I just put these values, so it turns out to be 1 minus TL over TH. Okay, and this is the equation which is same for the Carnot cycle as well. So this is the required thing for example 9-4, that we have to prove that the efficiency of the Ericsson cycle is equal to the Carnot cycle efficiency. So in the similar procedure, if you have to develop the equation for the Stirling cycle, so for that you just have to put the equation 9 dash 7 dash 32. Okay, I have put 7 dash 31 because it is in terms of pressure, and you have to use if you have to find out the Stirling cycle in terms of volume equation, which is 7 dash 32. So you can easily find that if you can solve it, it turns out to be equal to TL over TH. Okay, so this is the example 9-4. So if you have any question, you can ask me, then we will move towards the next question. Okay, so first you have to read the statement. So this is 9-65 from your book. And the question is that consider an ideal Ericsson cycle with air as the working fluid executed in a steady flow system. Air is at 27 degrees C and 120 kilopascal at the beginning of isothermal compression process. So if you can notice from the TS diagram for the Ericsson cycle, you can easily find that this is the state number 3 which we are talking about. That start of compression is at, so this value is T3 and this value is P3. And then during which 150 kilojoule per kg of heat is rejected. So it's mean that Q34 is given in your question, which is the rejection amount, and heat transfer to air occurs at 1200 Kelvin. So the highest temperature is given. So if you can just correlate with the TS diagram, so you can find out that this is the temperature at point number 1 and temperature at point number 2. So determine the maximum pressure in the cycle. So maximum pressure is at point number 4. I just correlate with the PV diagram, and the net work output per unit mass of the air we have to find, and thermal efficiency of the cycle we have to find. So we have to note down the data and we will move towards solution. So the TS diagram of Ericsson cycle is over there. Okay, so from the part A, so you have to find the pressure at point number 4. Okay, so at this point your pressure is maximum. Okay, so now we can apply one relation, which is we already know that Q is equal to T delta S from the previous example, and from here we can say that S4 minus S3 is equal to Q, and this Q is the rejected part because it is we are talking about between 3 to 4, so this is Q out, and the temperature we are talking about is at the TL. Okay, and the TL is given in your question that the minimum temperature is 300 Kelvin and the maximum temperature is 1200 Kelvin from your problem statement. Okay, so from here we can easily find the value of S4 minus S3 because Q out is known to us from the question and TL is known to us. So I can simply put the values, that is minus 150, and also this is minus because we are talking about the rejection process. So minus 150 and 300, and if we can solve it, it turns out to be minus 0.5 kilojoule per kg torque. So this S4 minus S3 is known to us. So now we can easily apply the equation, which is 7-31. Okay, so which we already discussed about that these equation are valid for isothermal processes. So S4 minus S3 is equal to Cp log of T4 over T3. Okay, because we are talking about the rejected part, so that's why we are interested in 4 to 3 point, and minus log of R log of P4 over P3. As it is isothermal process, so it is eliminated. And now we have to find the value of P4, and P3 is given to us from the problem statement. S4 as minus S3 we have already found in this step. Okay, so if we can solve it, then 0.5 is equal to minus 0.287 is the value of R gas constant, log of P4, and P3 value is 120 kilopascal from your problem. So simply solve it for P4 and you will get the value of P4 as 685.2 kilopascal. Okay, this is the solution of part number A. So now coming to the solution of part number B. So in the solution of part number B, we have to find the total work, which is W net. So for W net, you already know that W net is equal to Q in minus Q out. Okay, so now Q out is known to us. Q in we have to find. Okay, so in order to find Q in, okay, so you already know that Q out over Q in for the Ericsson cycle is equal to TL over TH. Okay, we just compare the Carnot cycle efficiency with the efficiency of the Ericsson cycle, so it's become equation like this. Okay, so from here we can say Q in is equal to TH over TL into Q out. Okay, so now TH value is known to us from the question. It is 1200, TL is 300, and Q out is 150. Okay, so simply we can put the values and we can find the value of Q in as 600 kilojoule per kg. Okay, so now we have the value of Q in with us, so we can simply put the value over there, and Q out, the value is from the question, so 150, and from here we can easily find the W net, which is 450 kilojoule per kg. Okay, so this is solution for your part number B. So you have to note it down, then we move towards the next part. If you have any question, you can also ask me. Okay, so now your C part is to find the thermal efficiency. For thermal efficiency, we already know it is equal to the efficiency of Carnot cycle, so TL over TH. So simply just you have to put the values of TL as 300 Kelvin and TH as 1200 Kelvin. Okay, and you can solve it. It turns out to be 0.75 equal to 75% for your thermal efficiency of the Carnot cycle. Okay, so now the solution of your 9-65 is completed. So if you have any question, you can ask me, and then we move towards the next question. So now this is the problem 9-66 from your book. So if you can just read the statement, an ideal Stirling engine using helium as a working fluid. Okay, so here it is mentioned that helium is the working fluid, so you have to find out the properties of helium from table A2. Between the temperature limit of 300 and 2000 Kelvin. So it means that lower temperature is 300 and highest temperature is 2000 Kelvin, and pressure limit of 150 kilopascal. So your lower pressure is 150 and the highest pressure in the cycle is 3 megapascal. Assuming the mass of the helium used in the cycle is 0.12 kg, so mass fraction is given. So in the A part, thermal efficiency of the cycle, we have to find the amount of heat transfer in the regenerator, we have to find, and the work output per cycle. You have to return. So you have to note down the statement and then we'll move towards the solution. Okay, so again starting from the TS diagram for the Stirling cycle. So in Stirling cycle, you know that 1 to 2 is the isothermal process, then 2 to 3 is the constant volume regeneration process, then 3 to 4 is the isothermal heat rejection process, and also the compression process, and then 4 to 1 is the constant volume regeneration process again. Okay, so in the part number A, okay, first we have to find the properties of the helium. Okay, so for helium properties, so you just have to go to table A-2, okay, and find out that the value of R, which is the gas constant, is 2.0769 kilojoule per kg dot Kelvin, and then also you need the value of CV in order to find the regeneration, which is in the part number B. Okay, so CV value is 3.1156 kilojoule per kg dot Kelvin. And in your question it is mentioned that the temperature limit is 300 Kelvin for the lowest one, and the highest temperature is at 2000 Kelvin. Okay, so in the part number A, simply we have to find the thermal efficiency. So thermal efficiency, if we know the highest temperature and the lowest temperature, so simply you can use the TL or TH, and by just plugging all the value, you can easily find the value of thermal efficiency. And that turns out to be 85%. So this is the part number A. So in the part number B, what we are interested in, the amount of heat transfer in the regenerator. So we already know that amount of heat transfer regenerator is from 2 to 3 towards 4 to 1. Okay, so we are interested in the queuing between 4 to 1. Okay, as it is a constant volume process, so we can say that Q 41 in is equal to mCV T1 minus T2. Okay, so it is a constant volume process. So M value is given in your question, which is 0.12. CV value we can get from table A2. T1 value is known to us from the problem statement. T4 value is also known to us. Okay, so we can just simply put the values. T1 is 2000 and then 3. And if you can just solve it, it turns out to be 635.6 kg of your Q4 in 41 in. Now coming towards part number C. So in the part number C, we have to find the W net. So for W net, you already know that it is equal to efficiency into Qing. So efficiency we have already find in the part A. So Qing we have to find. Okay, so in order to find Qing, we already know that Qing is equal to M, because it is at the highest temperature and between state number 0.2 and state 1 S1. Is it dropping? Okay, so now the issue is that we do not have the value of S2 minus S1 with us. Okay, so first we have to find the value of S2 minus S1. Okay, Okay, so in order to find S2 minus S1, we can simply say S2 minus S1 is equal to R log of V2 over V1. Okay, this comes from your equation 7-32, which I already told you, and that is valid for isothermal process, which is in terms of volume now. Okay, so now the issue is again that we do not have the value of V2 over V1 also with us. Okay, we have the value of R, but we have to find V2 over V1 first. Okay, so in order to find the value of V2 over V1, we can simply apply the relation between state number 3 and 1, because these are isotropic processes, not isotropic processes. So we can simply say that P3 V3 over T3 is equal to P1 V1 over T1. Okay, so if we can just rearrange this equation for V3 over V1, it's turned out to be P3 P1 over T1 P3. And from the PV diagram, if you can just correlate the Stirling cycle PV diagram, so you can easily say that V3 is equal to V2. Okay, so from here, because T3 is known to us from the question, T1 is known to us from the question, and T1 is also mentioned in the problem statement, T3 is also mentioned in the question. So V2 over V1 is equal to, okay, if I just put all the value, which is 300 Kelvin, T1 value is 3000, and T1 value is 2000, and T3 value is 150 kilopascal. So it turns out to be 3. Now V2 or V1 is known to us, so we can easily find the value from of S2 minus S1 from this equation. So if I can put the value of R for the helium, so it will be 0.0769, which we already get from the table A2, and then simply log of 3. Okay, and if we can just solve it, it turns out to be 2.282 kilojoule per kg per Kelvin. Okay, this is the value for you S2 minus S1 is known to us. Okay, so now S2 minus S1 is known, so we can simply put the value into this equation. So 0.12, highest temperature is 2000 Kelvin, and S2 minus S1 we have just signed the previous step, which is 2.28. Okay, and if we can solve it, it comes out to be 547.6 kilojoule of your Qin. So now Qin is known to us, so we can easily find the value of Wnet, because efficiency is known to us from part number A, 0.85, and Qin is 547.6. Okay, and by using by multiplication, we can just find the value 465.5. Okay, this is the solution for your part number C. Okay, so if you have any question, you can ask. Okay, you can note down the question and then we will move to the next slide.
No questions, sir. It's clear. Thank you.
Okay. Okay, so now coming towards the question which you have to solve. Okay, so it is a very simple question. I already solved in the, which is 9-65. So only the data is different. So consider an ideal Dixon cycle with air as a working fluid executed in a steady flow system. Air is at 30 and 140 kilopascal at the beginning of compression process. So it's known P3 and P3 is known to you. 125 kilojoule per kg of heat is injected. So Q34 is known to you in the question, and heat transfer to air occurs at 1400 Kelvin. So highest temperature is mentioned. The maximum pressure you have to find. So P4, and the net work output per unit mass of the air and thermal efficiency of the cycle. Okay, so this is a question you have to solve, and all the students who will send it to me in a clear way and with a good presentation, they will get 0.2 absolute mark, and you can take the time as per your convenience. Okay, so there is no time limit, but definitely you have to send it to me, otherwise you will lose the absolute mark of 0.2. So you have to note down the question or data, then we will just stop the lecture at this point.
Sir, how much time do we have?
There is no time limit for this. You have to just follow your convenience, and you can take 1 day, you can take 2 days. Okay, so it's up to you. But the main thing is that all the students
Okay, sir.
must
Thank you.
ensure that if they are not sending the assignment that I have assigned at the end of the lecture, so it's mean that they are losing 0.2 absolute marks. And if any student has not sent it to me any assignment, so it's mean at the end of your course you will straightforward lose 6 absolute marks from your total marks. So this reflect that there will be a decrease of your grade up to 2 marks. Okay, so if you are getting B, so you will straightforward get towards the C plus or C. Okay, so you have to take care about it that you have to send it to me on a regular basis.